Welcome back to my chemistry lessons. Today we are going to discuss about the rate of a chemical reaction. So what do you mean by a rate of a chemical reaction? So rate of a chemical reaction means is the velocity or the speed of a chemical reaction that taking place. So we can also define it as a rate of a chemical reaction in terms of concentration and time. That means the change in concentration of a reactants with per unit time. That might be in the case of reactants, there is a decrease in concentration of reactants with respect to time. When we consider the case of products, there is an increase in the concentration of products with time. So when we are saying one reaction is taking place slow or fast depends upon the change in concentration of reactants or products. So when we take an example like A2 plus B2 gives 2AB. So here A2 and B2 are reactants and 2AB, that means the products. So when we plot a graph against energy against the progress of reaction, we can see that this point of the graph stands the energy of reactants, and when that reaction undergoes the process, we get a curve like this, and it's end up here into the energy of the products. So EP means the energy of the products. So in between the transformation from reactants to products, there is a complex stage formation of reactants, and when we consider this reaction, the reactants has higher energy than products. So during the transition of or transformation of reactants into the products, in between there is a chance of formation of a complex, an activated complex formation takes place. So what is activated complex formation? So during a chemical reaction, it starts from reactants and ends up in the formation of products. In the middle of that process, some of the reactants try to break their bonds, and some of the new bonds form between two individual reactants. So there is a transition stage. Some of the bond breaking takes place, at the same time some new bonds formation also takes place. That transition state of reactants and products is known as a activated complex formation. So the activated complex have always higher energy than reactants and products. So once reactants attain that state, that reactants will be formed into products later on. So the transition state is a very important stage, very energetic state. In that state, many new bonds are forming. At the same time, many bonds between the reactants starts to lose. So from the previous discussion, we came to know the rate of a chemical reaction is directly proportional to the concentration of reactants we are using. So in that concept, we try to explain the mathematical form of a rate of a chemical reaction. So for example, if you take an example like A into B, here A is the reactants and B is the product. So here the concentration, the square bracket of A, the molar concentration of capital A at a time T is equal to 0, that means in the beginning of the reaction. So there is no change in concentration of reactant A at that time. At that time, the change of concentration of reactant A is taken as the initial concentration of reactant. So at a particular time T is equal to 0, the molar concentration of A is equal to small a. That means initial concentration of reactants. After some time, after t seconds, the reaction undergo process and how much reactants left at that time. That means t seconds. So at particular that time, t seconds, the concentration of reactant A is A minus X. So the rate of a chemical reaction is equal to the change in concentration of A divided by the time. So we can write like that: the rate is equal to change in molar concentration of reactants by time taken for that change. So the rate is equal to dA divided by dt. So that's equal to dA minus X divided by dt, because A is equal to A minus X. So that's a mathematical derivation form of a rate of a chemical reaction. Rate is equal to dAx by dt. So when we compare to the volume of A with respect to X, A is very higher, very bulk compared to the small x. So in that case, so when we take this expression, rate is equal to dA divided by dt is equal to the change in the case of reactant, if there is a decrease in concentration of reactant with respect to time, so that we are using negative. So the volume of A is bigger than X, so we can neglect the change of in the change in concentration of capital A. So we will write the expression the rate is equal to dx by dt, because when we compare to the initial concentration, that change is negligible. So rate of a chemical reaction is equal to dx by dt. So next, we are going to discuss what are the factors affecting the rate of a chemical reaction. So there are 5 factors generally affecting the rate of a chemical reaction. The first one, the nature of reactant. Second, the particle size. Third, the concentration of reactants. Fourth, the temperature. And the fifth, catalyst. So what do you mean by the nature of reactants? So when we are using the reactants might be in covalent molecules or ionic molecules. So if it is a covalent nature reactants, the strong covalent bonds need to be break before the product formation. So that will consume more energy. So if you are using the reactants with the covalent bonds, that kind of reaction needs more energy, and that reaction will be slow in the beginning. So if you are using ionic molecules as a reactants, so that reaction will be much faster than covalent molecules. The second point is the particle size. So particle size also has an important role in the rate of a chemical reaction. So if you are using the powdered, very finely powdered particle size of reactant, so that could increase the surface area of the reactants. So according to the kinetic theory of the collision, the number of effective collisions will increase, and as the number of effective collisions increases, the rate of the product formation also. So the finely divided particle size of reactants are much faster than big sized particles of reactants. So in order to increase the rate of reaction, the best way is to use the final powdered form of the reactants. The third is the concentration. So as we know, as we increase the number of moles of reactants, that means concentration of reactants, the number of effective collisions will increase. So naturally that will increase the rate of chemical reaction. So the fourth point is temperature. So mostly all the chemical reactions from the reactant to products formation are considered to be endothermic reactions generally. So the increase of temperature will help to increase the rate of a chemical reaction. The last point, the catalyst. The catalyst has a very important role in the rate of a chemical reaction. So in this point, we have to know what is meant by a catalyst. So catalysts are such a substance we are using to alter the speed of a chemical reaction. But these catalysts are never be involved in that chemical reaction, such as chemical changes or something like that. So catalysts can alter or increase the rate of chemical reaction without involving chemically in that reaction. So what is the role of a catalyst in a chemical reaction? The catalysts are helping to create a new energy path to reactants to products. So generally, according to kinetic theory of the collision, the catalysts are lower the energy, the energy barrier to activated complex. So many of the reactants can pass through the barrier, and they can be easily formed into products. So the role of a catalyst in a chemical reaction is they are reducing or minimizing the height of the energy barrier to form the activated complex. So when we are discussing a role of a catalyst in a chemical reaction, so this is very easy to understand with the help of this diagram. When we plot energy against the progress of a reaction, in the case of A2 plus B2 gives 2AB as a product. So here, this reaction we have seen earlier, and that was a solid curve. That solid curve was representing the reaction path without catalyst. So when we are adding a catalyst, a new reaction path will be formed. That indicates a dotted line. So from this graph, it is easy to understand what happened to the energy barrier. In the previous case, the energy barrier was this much big, and when we add the catalyst, when we added the catalyst, the new reaction path formed with a low energy barrier. So the activation energy with the addition of catalyst indicates EAC. So here, more number of reactants can overcome this barrier and become the products. So here, delta E, that means the change of energy between products and reactant, or we can call it as a heat of a reaction. So these are the typical points about the rate of a chemical reaction. So as part of the rate of chemical reaction, I would like to also discuss about the order of a chemical reaction and molecularity of a chemical reaction. So what is meant by order of a chemical reaction? Order of a chemical reaction is a sum of the powers of molar concentrations involved in a rate determining step of a chemical reaction. So in a chemical reaction, there are many steps will be involved. So few of the steps are determining the rate of a chemical reaction. In that rate determining step, how many reactant molecules involved, and the sum of that powers of the molar concentration of reactants is known as the order of a chemical reaction. So when we take a general example like this, AA plus BB plus CC gives products. So in that case, according to rate law of expression, is rate is equal to K molar concentration of A to the power A molar concentration of B to the power B, molar concentration of C to the power C. So here this is the rate of that particular chemical reaction. So here the power terms A to the power A, B to the power B, C to the power C. So according to the order of a chemical definition of order of a chemical reaction, the order is equal to sum of these two components. So order of that particular chemical reaction is A plus B plus C. So next, what is the molecularity of a chemical reaction? Molecularity of a chemical reaction is the number of reaction species involved in a chemical reaction. So in this case, the number of chemical reactants involved in this chemical reaction are A, B, C. So the order and molecularity of this particular reaction is same. So when we take an example, very interesting example, the hydrolysis of ethyl acetate with the water. So what happens to the ethyl acetate during the hydrolysis? So on the board, this is a very special example of the molecularity of a chemical reaction. Could be vary from the order of that particular chemical reaction. So that means order and molecularity may not be same all the times. On this particular example, if you see the hydrolysis of ethyl acetate, this is an ethyl acetate. During the hydrolysis, what happened is there is a breakage of bond here takes place. So water, we can write like this, HOH. So water can be write like this, hydrogen part and OH part. So during this hydrolysis, what happens there this OC bond breaks, and the H goes to mostly negative oxygen atom, and OH goes to mostly electropositive carbon atom. So we will get C2H5OH and CH3OOH. So we will get the product as acetic acid and ethanol. So during this reaction, the volume of the water used in this chemical reaction is in a bulk. So in that bulk amount, very feeble amount of water is using for that particular hydrolysis. So the change in concentration of water is negligible. So that is not coming into the picture of the rate of chemical reaction. So in that case, the rate of chemical reaction only depends on the concentration of acetic acid. So in that case, the order of a chemical reaction is 1. At the same time, there are 2 molecules involved in the chemical reaction. So the molecularity of a chemical reaction can be considered as a 2. So in this case, order is 1 and molecularity is 2.